to germline at all. So those are two issues, the second of which will come up again. So there are lots of different approaches to gene transfer, right? You can do it somatically, which is the delivery of a transgene to treat a patient. Historically, we've been doing this for quite some time. Historically, this was used for single gene defects, but that has been expanding over time. Again, we've been doing this for many decades. The first trial was for adenosine deaminase deficiency in SCID, which led actually to some complications. We ended up giving the kid, like curing them of SCID, but giving them cancer, which caused problems in the gene transfer field for a long time. Sort of, it went quiescent for a bit. But now we have learned enough that it's actually quite safe, relatively speaking, and there are hundreds of clinical trials. In the US, historically, again, the oversight for gene transfer trials was done primarily by the Recombinant DNA Advisory Committee, or the RAC, because scientists are bad at naming things. And the RAC was originally established when we first learned to cut and paste DNA in the 1970s, and was designed to review recombinant DNA experiments when we didn't have a lot of experience with that. It evolved over time into the body that reviewed transgene gene transfer trial proposals, and it's now evolved even further into NextRAC, although I don't actually know if it still exists. I haven't heard that it's been disbanded, but given what I know about things today, it's entirely possible it's been disbanded. The Office of Human Research Protections has been disbanded, as has the Secretary Advisory Committee for Human Research Protections. No longer exists. So, unclear. But I haven't heard anything about NextRAC in particular. But anyways, so this, again, this body was originally for a particular kind of science, and I guess because of what I said at the beginning, I'll make this point, right? This is an example of the RAC.
Yeah, and this bond mandated by Congress by law.
No. No, they are advisory, most of them are advisory to the NIH director,
So
or advisory to the Secretary of HHS. There's a lot more to say there, but.
But I just want to see, I just want to know where we stand in terms of actual law.
Yes.
But those are basically the discussion of the executive, so.
Yes. Yes. Although OHRP, the Office of Human Research Protections, that office, I'm not actually sure. The Secretary's Advisory Committees are at the discretion this time, but I don't know about OHRP. That is a good question. And I don't know if there's legal action to. I know there's legal action brewing about SACHARP, because the folks who've been dismissed from NIH advisory committees are non-random. It's mostly women and brown people. So there is legal action brewing there, but I don't know what's good status is. This is a very, very strange time to.
Well, it's a good time to think about things.
Yeah. I mean, I think well, again,
Yeah.
whole other conversation, but I'm very happy to have all those conversations about what we would like to see the other side of this, and what would be best possible governance mechanisms for these kinds of science and for human research protections generally. I think those are conversations we should be having right now. So the point I was making here is that this governance mechanism, the RAC, was originally designed to do one thing, which was review recombinant DNA research when there were lots of fears about what that would lead to, and concerns about the risks without fully appreciating all the benefits. We gained enough experience with that to understand that it was fairly safe. So the governance mechanism evolved to review. It's not like it solved all the problems, but we collected enough data, we understood the safety, the risk and benefits of the science, and we were able to move on, right? And the review of recombinant DNA left the RAC and went to the institutions that do it. So now we have biosafety committees. And you have to go and you say, I'm going to be using these things, and they say, yes, you are, you have our approval. And it's a much different, lower level of review than it was when we didn't understand the risks. So, moved on from recombinant DNA to gene transfer trials. And now, because again, we've gained enough experience with gene transfer trials to better understand the risks and benefits, that a centralized body no longer does that. It can go to the IRBs and the institutional review boards at institutions doing the work. And so the governance mechanism, again, evolved to be now NextRac, which, again, was advisory to the director of the NIH and is designed to sort of do horizon scanning and figure out what's next, and to try to stay at least in step with the science, if not ahead of the science, as it evolves. So, genetic modification technologies, of course, have also evolved, which is why we're having this conversation. So zinc finger nucleases and talents have been around for quite some time. CRISPR, of course, has now been around for over 10 years, but it was a dramatic advance in genome editing technologies. Because historically, like when I was an undergrad and doing yeast genetics, the way we induced mutations was to irradiate, to put the yeast under UV light and then select for the things that were funny enough that we wanted to study them, right? Humans don't like it when you do that to them. They like more precise technologies, and these genome editing technologies enabled us to go from this sort of scattershot approach, or just finding, sort of treasuring your exceptions, and in fact able to make much more specific changes. This is done in the case of CRISPR through either non-homologous, historically, again in CRISPR 1, version 1, through non-homologous end joining or homology-directed replacement, basically inducing a double-stranded break and then fixing it in various ways.
They had a lecture from Fred.
What?
They had a lecture from Greg.
Oh, good. Good. Yeah, so you understand this. So, so I won't go through this. In fact, I'll skip straight through. Because when I started giving this lecture, Greg wasn't here.
Yeah, no, but you can read it out, but.
I mean, as my children know, my freshman speech comm teacher taught me replication is necessary for human comprehension. Right. So like,
that's where it's from.
Oh, really?
There's a saying in Latin that says, repetita
Ah, yeah. Mm-hmm. So I say it over and over to my children, so now they repeat it back. And my kid's about to go to college, so she will tell all her, and thus it will be repeated forevermore. Okay. So, I talked about gene transfer. You heard from Greg about the science behind genome editing. It can, of course, be done somatically or in the germline, right? It's somatic in a person in front of you, or in egg, sperm, embryos. It can be used for reverse genetics, right? So that you, as opposed to identifying a phenotype and studying it, you can induce changes and then see, like, break things and see what, what's going on there. It's been used for gene therapy, now a number of things. In fact, FDA just approved a treatment on Friday, I think, for the connective tissue disorder where your skin.
Oh, is it blistering?
Yeah, the blister, something bullosa. I'm blanking on the first word.
Pemphigus?
What?
Pemphigus?
But it's a topical treatment that you can apply for blistering skin disease, right?
I think it's topical, yeah. Yeah, all that's in my head is retinitis pigmentosa, which is like not it at all. Yes, that. Yes, thank you. And then, of course, it can also be used for human germline genetic modification. Again, this is a much, much more specific technology than we've had in the past. But there's still some off-target effects and concerns about mosaicism, meaning that the target population of cells, they don't all get the change you want. But another sort of point that I want to make about how science evolves here is that, this happens across multiple fields, that you have an area of science. At first, there are high barriers to entry, right? And then there's some change, like some radical change in the science that enables many, many more people to get involved, and so the science evolves much, much more rapidly. This happened in stem cell science when we went from embryonic stem cell research that required human embryos, which are rare and precious and hard to get for research purposes, to induced pluripotent stem cells, where suddenly all you needed was a skin sample or a blood sample. And tons of researchers flooded into the field because the barrier to entry went down and protocols evolved and the science evolved really rapidly. The same thing happened here when we went from talons and zinc finger nucleases, which were like expensive and labor intensive and bespoke and took a lot of expertise to construct, and really were constructing them, to CRISPR, where all you have to do is you order the guide RNA. And so many, many more scientists were able to get into the field, and protocols evolved really, really rapidly. And this is Layla, who was the first to get a gene-modified CAR T cell treatment for cancer. Genome editing also, at the beginning, was overseen by the RAC, as well as FDA. However, it had been for years in the guidelines of the RAC that the RAC will not entertain proposals for germline alterations, but will consider proposals for somatic transfer. And the FDA said that an investigational new drug license would be required before somatic or germline applications were attempted in humans. And I will come back to that in a second. The other bit that I want to mention that I don't think has been used in any germline experiments thus far, but is yet another evolution of the science that's important for the story, is epigenome editing, right? We now can use those same tools have been, as I'm sure Greg told you, right, are now, you can use them in a way that doesn't induce double-stranded breaks and doesn't invoke DNA repair mechanisms, which changes the safety profile of the thing, right? If you're not breaking DNA, that inherently is better. Like, you're not creating mutations of that sort. It enables new kinds of study and intervention with broad translational potential. Again, more likely at the somatic level than at the genome or at the germline level, but I didn't want to not talk about it. All right, so going back to genome editing oversight, in particular at the germline level, as I said, the RAC, which doesn't exist anymore, and the FDA would have oversight over germline genome editing. But in the fiscal year 16 appropriations bill to FDA, so bill from Congress that gives FDA its money, at the last minute added this rider that said that we're giving FDA slightly more money, but with this money, they are not allowed to evaluate or even acknowledge receipt of an application to do germline genetic modification. They can't even say if someone's asked them to do it. So it's effectively banned. And in fact, all of the countries that had relevant policy banned germline genetic modification. These policies fall under a range of different kinds of policies, including basic science, reproductive medicine, and gene therapy. And this is where we come back to that distinction between what counts as germline. Yeah.
And since fiscal 2015, they continued with that wording?
Yeah. Yeah. The tricky bit about Congress is once something's done, it's very hard to undo, unless you're just like getting rid of FDA. So, yeah. And all the folks I know at FDA don't have their jobs anymore, so I don't have anyone to ask either. So, I don't know. But that comment I made early in the lecture about whether changing mitochondrial DNA constitutes germline genetic modification is sort of came to a head, or was pushed on most in the UK, because in the UK they don't permit germline genome editing, but did want to allow mitochondrial transfer, which I'll come back to. So in the UK they have defined out of germline genetic modification mitochondrial transfer technologies, which again I'll come back to. Okay, so now we go back to this week in March 10 years ago when everyone was saying, don't do this. What actually were they saying? So the recommendations from Baltimore et al., which is this second paper. So the second paper is a group of academics, including both scientists and ethics types and policy people. So David Baltimore and Paul Berg were both involved in the Asilomar conference in the 1970s that established oversight, created the RAC and established oversight of recombinant DNA technology. Jennifer Doudna, of course, critical invented or discovered CRISPR initially. Alza Charo, Hank Freely are both ethics types. Keith is a scientist who's been deeply involved in policy for a very long time. So a group of academics saying, very interested in well-regulated science and enabling science to go forward. They strongly discouraged germline genetic modification attempts globally. They said that we should create expert forums for public education and discussion, and they encouraged support of basic research with CRISPR, and called for a convening of an Asilomar-like meeting for human germline genetic modification. Again, 2 of the people from Asilomar were part of this. So why do you think these are the recommendations they made? Thinking about the group of people that this was. This policy in the end is made by individuals with interests and personalities and goals in mind. So this is a group of academics. What's their goal?
They want to further use these tools and explore what they can do.
Further use these tools and?
To see what they can do, so they have a vested interest in defining the ethical limitations of what they can use these tools for.
Why does defining the ethical limitations help them use the tools?
if the public says, oh no, what have you done? They'll just cut off all CRISPR research.
So do you want to finish answering the question?
I was gonna say, so they can control the narrative with the public, interprets their use and like how these tools are being used, so they can get ahead of this like mob mentality.
Okay.
I'm kind of reminded of like, I don't remember how many years ago, it was like the end of the 90s, but the Jesse Gelsinger case, where, I think it was an AAV treatment, one of these early gene therapies, and he ended up, was the first person to die in a treatment. And he had like not a very serious condition, he was just allergic to red meat. He was like, I'd like to eat a steak, so they're like, why don't you do this trial? And eventually he died. And I think that sort of led to essentially, like, as already mentioned, this sort of public backlash. Like, oh, we can't give money to killing healthy people, right? And so if they can sort of like guide where they think it's safe to work, then the public will give more money, will support it, and then hopefully down the line there will be enough research to sort of make the leap and say, hey, pretty sure it's safe now, we're going to start like working in humans. But we got this far because we set up these guidelines for ourselves.
Mm-hmm. So it's both sort of controlling the narrative, but also giving themselves boundaries, right? So self-regulating in a way.
I think I remember, this was maybe 2018. I joined my first lab and we were doing gene editing. And I remember seeing an article, I can't remember which journal it was in. Basically, there was like competition between Chinese scientists, US scientists. So they would say, oh, we engineered the dog, and then they engineered the chimpanzee, and then they engineered the pig. So it was like, you start this kind of arms race, and then you have no control, and just a race to see who can, get to the germline first. Like that's where it was going, I think, at that time. And that's funny because this was after this was published. But we're still kind of like, it's like placing bets on who can get to the next organism faster. So.
I think one quick comment. I also feel like sometimes we forget this as scientists, but like we are not like self-sustainable. Like we must have public funding in order to do science. Like almost no scientist generates enough money to pay for their own research, right? And so it's important to maintain public support because otherwise, like it's just not possible. In almost any country, like I don't know if there's any large country that the majority of the research is not funded by public funding.
Yeah.
I don't know if you saw the chart. The teacher had a chart about the funding by country and relative to the world.
Yep.
And I, this game was like, should have been organic because when I think it used to be like this, Europe is like this. Yeah. And then China now is maybe the biggest. And that's one thing. It's germline. Once it's in germline, it's everywhere. Like, it's not, doesn't necessarily respect boundaries.
Yeah. And how do you get the public to trust you?
Show them the benefits of the work that you're doing.
Okay, yeah. Which requires talking to them, which is number 2 up there. Which scientists have only realized, many scientists have only realized in the last 3 months how critical that is.
I mean, I think even just about like, you get the Hopkins update, and every single Hopkins update since the new administration says research saves lives, and it has a little vignette for someone. And I think that's something that, I don't know if we've been arrogant, but we've been sort of like blind to like how much we rely on the public good to like do our work. And so it takes a lot of communication. I think it also takes like engaging, politicians and people who actually control the purse strings of these things.
So I will say, someone involved in this paper, I don't think I've told this group before. This is like my favorite anecdote about scientific communication to the public. At one of the early conferences that I will tell you about in just a little bit about CRISPR, a reporter asked, like, what do you think the public is going to think about all of this? And the eminent scientist said, you would have to talk to someone who's closer to the public than I am. So if that's the attitude of scientists, then we have a lot of work to do in terms of learning how to build relationships with the public, and so that they will listen to us when we tell them about the benefits of the work that we're doing. Yeah. And then,
I was gonna say, like, there's also just a lot of power when it comes to like science communications today, with like YouTube channels and whatnot that are dedicated to not only explaining current science as well as current law and current like ethics and whatnot, but also breaking it down in a way that's very digestible and in a way that's like actually has a lot of visual and a lot more engagement, whether it be in the comments or like the actual descriptions. So I do think there's at least improvement in that front,
Yeah.
of actually having a way for scientists to reach out and talk with people. I think it's more so, I guess, getting more cross talk to actually happen outside of the communication of what the science means. Now we can actually hear back from the public of, okay, this is how we're feeling about this. Can you help to rectify this gap up between?
yeah.
Oh, I was just gonna ask, do you think that the attitudes that previous generations of scientists have had, I mean, even if we go forward and have a more positive, open conversation with the public, do you think the damage that previous generations of scientists have done is kind of permanent now, given our current situation?
I don't think it's permanent, because just as science evolves, the communication technologies we have available to us evolve, attitudes evolve, right? And I mean, certainly the last 100 days has been a shock to the system, right? And honestly, to let the scientists off the hook a little bit, right? Our incentive structures do not align with talking to the public, right? We are not trained to do it, right? We are trained to communicate our science to each other, and we're really, really good at it. We are not trained to talk to the public. We are not incentivized to talk to the public. In academic science, you get grants, you write papers, right? You get 0 credit in the tenure and promotion process for giving a talk at a local library or church. You get 0 credit for spending your evening hours on Blue Sky or TikTok or wherever it is you might be communicating to broader audiences. So I think it's also on our academic incentive structures to evolve in response to the current moment as well. You and then.
I mean, like you said, like making it kind of like a way, making it so that we kind of have to communicate with the public more often and more frequently in order to, I guess, maintain job security and things like that. I mean, I absolutely support like talking to the public, but do you think that the public might think that we're now coming off as phony and fake in order to gain their love and affection for research and science?
I mean, they're living the same world we are. They see what's happening. So I mean, if there are scientists who are just figuring out now that we actually need to build a relationship with the public, welcome. I'm so glad you're here. Let's work. I think just have to move forward from where we are. Hang on.
I don't know about the broad group, but here at Compton, they're reevaluating the education track for promotion, where public interactions and things like talks at libraries and so on. It's a possibility that they're going to actually count points
That's fantastic.
towards promotion. So the university as a whole has these things in their mind.
That's great. I did not heard that. Thank you for joining.
I just want to return a little bit this concept that we are becoming very public, because the way the NIH was established, it was the government contracting our work because they wanted the work. The government is dependent on us. The people are dependent on us too to do the work. We're not here beggars. They ask us to do the work. I mean, so, you know, it's a contract. And they wanted it, and we provided the service. Now they say we don't like the service. Second, this problem with science is true also for a lot of other fields. Yeah, not just science, economists are saying, hey, this thing is going to be disastrous. And they probably say, no, it's great. Why? Because they feel it. And the same thing is happening.
Yes, I agree.
But they're not as dependent.
But they are not as dependent, and we need public bias. We need to be trustworthy, not only because we need the federal dollars to run our labs, but also because we're geneticists. The human genetics program, and which means we need human DNA. And people who don't trust us aren't going to want to be in the research either. So there are layers to our need to demonstrate trustworthy to our trustworthiness in general.
All right. Yep.
I mean, something to also keep in mind though is that like, well, definitely science right now is under fire. Like many other institutions that are reaching like the big like U.S. size scale, I feel like a lot of institutions already have their own things that have already also come back from those things or already have like some sort of image shifts or adapted, like the adaptations they've already made. So I feel like while the situation is definitely different for science community, science institution here, I feel like it's still definitely, we can come back to this if we just make the proper adaptations or make the right adjustments. I don't know. I don't think it's anywhere close to falling apart.
I think we're still only 100 days in I mean, yes, we need to adapt. Yes, science isn't perfect. And all of these other things are true as well. Yeah.
Also, how do we ensure that, like, you know, the relationship with the public matters, but also relationship with the press is like, we're ensuring that, you know, really important scientific discoveries that directly impact, like, maybe care or therapeutics are being prioritized, like, you know, communicating with the press. I mean, I feel like a lot of the bigger things that end up in the news are, oh, scientists are bringing back dire wolves, or they're trying to engineer dinosaurs. Like, so people in the general public are like, what are we paying them to do? Like, even though there's a lot of benefits, it's like, what's your relationship with the media as well? It's like they only really put out headlines that are like super controversial, but don't show, you know, this ASO that we developed that is like helping so many kids. Like, that's not being talked about.
I mean, not only sensational stuff, right?
Yeah, right, yeah.
And it also, interacting with the press is another thing that we are not incentivized to do at all. Yeah.
I think this is particularly a problem in basic science research, just because I think it would be interesting to do a breakdown of funding sources of here and then cancer research buildings. Because there are lots of labs and cancer research buildings who are almost entirely funded by private institutions or private individuals who are like, you know, I'm an oil magnate. I mean, I work in the David Koch cancer research building, right? I'm an oil magnate. Everybody sees that cancer is a problem. I'm happy to give my fortune to treat cancer. But basic scientists struggle to communicate. Like, I think the best example is like Ozempic, where it's like the basic scientists who were working on Gila monsters, why they were able to fast for like a month, probably were not communicating to the public because they just didn't know. But it's hard to say, like, I'm working on Gila monsters now, but it could become this miracle drug that treats a host of conditions.
Yeah.
That's gonna, you know, be the biggest, you know, pharmaceutical breakthrough in a decade. But you just have to, like, the public has to learn to have faith in these basic science, like, sort of like endeavors, even if it's hard to think, like, how does a Gila monster
and the
have to do human
scientists need to
human
learn
race?
how to tell compelling stories about that science. Yeah, that's what I was thinking. I was like, yeah, you can't. Of course, the press is going to grab onto like things that sound really cool and interesting. So we have to figure out a way to convey our science in a way that sounds cool and interesting. Like, dinosaurs are cool. Like, why would you not want to report about dinosaurs coming back? I mean, yes, the public's like, well, like, we don't need dinosaurs, but I mean, how do you make a story about using CRISPR to, like, I don't know, like, make people's hair grow longer sound as cool as bringing back dinosaurs? I think we just have to figure out a way to jazz it up without lying, without over promising things. But I think that comes with practice and patience.
And collaboration, I
Yeah.
would say. There are people who are very good at telling stories about these kinds of things, right? And scientists are, and again, I'm a basic scientist by training. I love scientists. We are a group of people who like get super excited and passionate about these tiny, like these small pieces of biological, like these structures and systems and everything. And y'all get really excited when talking about it. Like we need to figure out how to translate that enthusiasm and that passion into stories that are understandable by the public. So, okay.
I think it's funny. Sorry, so I had mentioned, but like George Church is an author on this paper,
Yeah.
which is like
Master storyteller
right,
and publicizer of George Church's science.
yeah, and he's probably not hurting for money, and so like this idea of telling stories and doing science that you may not necessarily agree with, it is working for him.
Yep, for sure. But again, there are teams of folks and entire disciplines who are good at storytelling and good at crafting compelling narratives and creating media that is both honest and clear and engaging.
Do you think that it would, in undergrad when we are taking our science classes, we are required to take arts and humanities and things like that. Do you think as we go up in science that should also be incorporated into the curriculum, like creative writing classes and just like our public speaking classes, just in general and things like that?
I mean, I love that. I'm biased. I'm a song and dance kid. And I have a kid who's going to college for theater. So I may be like on one end of the spectrum here. I mean, public speaking, absolutely. Right? Absolutely. We need to learn to, translating our science, right, we're the weird ones, right? Like we speak a particular language that is the scientific jargon that is very understandable to everyone in this room, but completely impenetrable to people outside this room. And we think that if we translate it into words they can understand, that it's dumbing it down. It's not, it's translating it from one language into another language, right? And learning, and that is a skill, right? To do it in a way that is honest and not misleading, but communicates the important information in a way that folks who are not in your special area of science can understand it. And if that's through creative writing, if that's through public speaking, great, but it's a skill that we can learn. Yeah.
This is maybe a cynical take, but I guess, do you think it matters as much if the public is not actually trained to understand how to critically appreciate the things that are being translated to them, if that makes sense? I think a lot about open access journals.
Yep.
And while it could potentially do a lot of good, it doesn't, to me, I guess, I don't know if it matters if the public cannot also understand what is actually occurring and has the ability to hold in an objective sense versus their own biases and their own limitations in education and that kind of thing. So I don't know if you've seen.
I think open access journals benefit people at academic institutions who don't have access to those to lots of other journals, not so much the public. I think that scientists have our own biases and limitations in terms of what we understand. folks are experts in their own lives and their own experiences, and we don't have access to that. And like the person I quoted earlier, like there's often a great distance between us in our bubble and them in their bubble. I agree that communicating our science more effectively and more often is not going to solve the problem. Right? There are other systemic challenges, but it has to be part of the solution. Right? Like we can't solve all the problems. Scientists aren't responsible for solving all the problems, but we are responsible for solving the problems we have control over, and this is one of them. All right. So this is the second paper by Lanphier et al. This is a group of people from pharma, from biotech companies. What are their goals and interests?
Making sure that the applications are safe for patients.
Yeah. Which goes back to the money. Right? They want to protect the market that they're trying to build in somatic editing. Right? So the best way for them to do that is to completely eliminate anything in the germline space so that germline mucking around doesn't lead to, as I think you said earlier, like wholesale banning of the thing. Right?
But also, in some ways, they don't want it to replace what they're doing.
Right. Yeah. Yep. And then the ISSCR, which again, International Society of Stem Cell Research, called for a moratorium internationally to use this for clinically. Said that scientists currently lack the understanding, it's not safe, and deeper and more rigorous deliberation on the ethical, legal, societal implications of any attempts are essential if this clinical practice is ever to be sanctioned. Again, this is a group of academics, so everything we talked about earlier with that first group, with the Baltimore et al. Paper, plus the ISSCR had this experience of battling what I call scam cell clinics. So these clinics all over in the US and all over the world who are willing to advertise they will inject you with stem cell treatments that will cure everything under the sun. And they had tried repeatedly to sort of combat that practice and got like cease and desist letters from the lawyers at these places. This is a professional society. They do not have deep pockets, so they had to basically stop that, and they don't want that to happen again in this space. And then finally, the NIH, Francis Collins was the head of it at the time, said, and by the way, NIH isn't going to fund this work anyway. But this is not the first time we've had this conversation. We've been talking about germline genome editing for a very, very long time. So this is the first federal report on the social and ethical issues of genetic engineering with human beings, which was developed by a presidential commission and published in 1982. So I was 8. Genetic technique could shape future generations. Ethicists wary over new gene techniques consequences. These are Gina Colada from 1994 for the New York Times. We've been talking about this for a long time. Every time there's a new technology that gets us a little bit closer, we talk about it. So in all of those last rounds, what did we come to? What were the concerns? Safety first and foremost, right? We had no technology that was safe enough to even consider implementing. Concerns about informed consent. How do you do informed consent when the product of the research is a human? What does consent look like in that context? particularly for the first, second, third, fourth experiment. Concerns about a right to an open future, right? Whenever this happens, we're doing it based on the information we have available to us today and the societal norms today and our conceptions of the good life today. And we're fixing those through genetic technology in the next generation in a way that raises concerns. Concerns about designer babies and commodification, right? That if you, you would have to do this in the context of in vitro fertilization. That's already $10,000, $12,000. Add pre-implantation genetic testing on top of that. It's another $3,000, and then whatever this is going to cost, let's say $20,000 a round. Let's say it takes you a couple of rounds, which is not unusual. You have a kid that you've paid $40,000 for to be exactly the way you wanted them with this genetic modification. How does that impact the relationship between the parent and the kid, particularly if the kid doesn't turn out the way you wanted? Concerns about distributive justice. Who's going to have access to this? Right? People who already have access to advanced reproductive technologies, the information necessary to even know that this is an option, to know that they have something that they want in their genomes that they want changed in the next generation, et cetera. And then concerns about the treatment versus enhancement debate, which is a debate we've had in this space for a very long time. But like, what constitutes medical treatment and is appropriate to the medical profession, and what constitutes enhancement, right? Which is absolutely raised in this context. And the conclusion in all these prior rounds was don't do it today. But it was mostly based on the safety concerns, right? So the other concerns, we didn't have to grapple with them as much because we just didn't have a technology that was safe enough and effective. And then, of course, CRISPR came along, right? It's relatively easy compared to zinc finger nucleases and talons. It's relatively inexpensive. Science is way bigger. We go to 11:30 or 11:45. When did we? 12 to 12. Okay, great. Science is way bigger. In the 1970s, when we were first able to cut and paste DNA, and the Asilomar conference was held to figure out what the heck to do about all of those things we talked about public perception and risks and benefit and self-regulation, et cetera. There were about 120, 140 people in the room, and it was basically everyone in the whole world doing that science. That's not what we've got today, right? Science is much bigger. Also, at the time the RAC was created, that model was replicated in country after country doing this science. The US model was imported elsewhere. Again, science is much bigger today. That's not how it works anymore. Different societies have different norms and conceptions of the good and ideas about what appropriate regulation of science is. The rest of science and medicine has also advanced, right? It's $1,000 to sequence a genome. We have all kinds of PGT, pre-implantation genetic testing that we can do. We know a lot more, and now we have AI to help us design in ways that we couldn't design before. And there are advocates, right? Even in the, right after CRISPR came out in 12, 13, 14, if I gave talks about this in a public forum, people would come up to me afterward and say, my family has this terrible disease and we need this science now because this is killing us. Please, please give it to us, right? So it's just a very, very different situation than those prior rounds of thinking about this science. And so lots of folks jumped into this space to try to grapple with all of these issues and try to come to consensus on not only what safety looks like for CRISPR, but all of those other downstream ethical issues. Hingston Group is starred because I lead that. So I have been in this space since very early. The first the first international, one of the first. The Kingston group was before this. But the National Academies hosted with National Academy of Science, National Academy of Medicine, the Royal Society from the UK, and the Chinese Academy of Sciences hosted an international summit in 2015 with global perspectives. And this summit led to a statement from the summit organizing committee, both about the science and ethics of germline genetic editing, but also establishing a new entity to look, international entity to look into these issues. That new consensus study met following the end of the summit. Again, this follows the Asilomar model. They had a meeting, the RAC was established and began meeting shortly thereafter. Yeah.
I'm just curious, like looking back since 2017, how much of an impact do these kind of reports have? Like, do the respective countries all sort of follow this and that's what guides their funding? Or is it just like, we made this report, yay, and then everyone goes home and nothing? I guess, what was your perception of that?
Yeah, that's a great question. And some of I'll tell part of that story as I go through some of these, but the most recent work that was done by the WHO is having trouble getting traction, because it is a big world and global regulation is hard because we're all different countries and different size societies and all the things I said before. There are efforts, like the later efforts tried to get much more concrete about things, because it is absolutely true that academics certainly, and the National Academies sometimes, has a habit of saying, here are the principles that should guide the things, and this yes and that no, but not giving like really concrete on the ground guidance about what needs to be done. They did eventually get there. And we have absolutely done that in the past, like with embryonic stem cell research, the National Academies produced a report that articulated a oversight structure that we all adopted. And it's the structure that we all still have and was ultimately adopted by the NIH. So we can do it. This space has proven to be challenging. That said, there have been, since Ho Jung Kwei, who I'll come to in a second, there haven't been additional announcements of babies one. So if the negative teaches us something, right, like we haven't seen it. So, I don't know. At least some level of efficacy and impact. So that was, so the National Academies consensus study followed the summit. They produced a report 2 years later in 2017 that said, it's not ready for prime time. Once we get there, it should only be used for really compelling purposes, like really high risk, immediately lethal, or debilitating diseases, not for enhancement, not for less serious things, not for adult onset things, but only for like the most compelling, devastating diseases that present early in life. Yeah.
So would this not be, like if you had Huntington's disease allele, this would not be included as an appropriate use of gene?
Correct. At least not in the first efforts, right? Maybe that's appropriate down the line. And certainly some of the patients who've come up to me after talks have been specifically talking about Huntington's disease. But there are also people that I've talked to with Huntington's disease who are like, I've had 50 years of excellent life. Like, why wouldn't I have wanted that, right? So there's a range of perspectives there. But yes, for this early report from 2017, Huntington's disease, I don't think would have cut it for early attempts. The following year, the Nuffield Council out of the UK issued a report on the technology, and they did something really interesting that I hadn't seen previously. I mean, they echoed lots of what was in the National Academy's report, but they offered these two governing principles, and it was the second one that was surprising to me, that any such interventions would uphold principles of social justice and solidarity. By this we mean that such interventions should not produce or exacerbate social division or marginalize or disadvantaged groups in society. I have never seen a recommendation report around a new technology evoke solidarity and social justice, so this felt like an advance to me. Of course, I think it's important to note that that is probably a bit easier to do in the UK than it is here in the US because they have a national health service. Everyone has access to health care. We do not have that here in the US. So social justice around anything having to do with health is harder for us because there's no guaranteed right to health care.
But also the NIH has basically sets the standard for everything. Yes. So it's like you're basically something covered by Medicare or not. Then all the other insurance copy, whatever that is.
Yeah, there's still
Yeah, there's
hundreds
still
of thousands of people without.
But
Any
basically,
health
the NHS would say, this is too expensive, nobody's getting it. But at least everybody's the same.
And nobody has access.
I mean, that's how it works in the socialized medicine countries. In Italy, if a drug is too expensive,
Oh,
you
yes.
cannot buy it.
Yeah, no, that's true.
Getting it, no matter
But
what.
it's not going to create social
No,
division if
right.
nobody has access. Yeah.
I mean, if you're really rich, you go and
You go somewhere else, yeah. So the second international summit, because science evolves, so the plan was to come back together to see how science had evolved and to have, revisit the guidelines that were produced in 2015, in 2017, at the end of 2018. But the night before this meeting, this guy hit the papers, and this is who I mentioned earlier, Ho-Jun Kwei. So he it was announced through a series of videos because he was about to get outed by a reporter that he had used CRISPR in germline, in embryos. Those embryos had been implanted in women, and that 2 babies had been born. So that second summit that had a whole agenda and speakers and all the things suddenly became about this.
Have you seen his Twitter?
No.
Oh, he has like a Twitter,
Oh, yeah.
like he said, ethics is holding back scientific innovation and progress on March 10th of this year.
I mean, a lot of his Twitter, his tweets are very.
His bio has 3 years in prison.
Yes, I have seen that.
Yeah, that's awesome.
you're like, what's last thing you said?
Interesting. 3 years in prison, which he got for this.
Oh.
Because, if you were to design an experiment that violates, all the ethical principles, what he did would be close. Well, you don't actually have time.
Well,
What?
well,
Yeah, until 12, so I have 20 minutes. So he didn't tell the hospital where he was working, what he was doing. He said he had ethics approval, he didn't. He told the people he was recruiting, the study was to introduce the delta CCR5, which is a mutation that protects people from contracting HIV. In China, couples in which one of the members has HIV cannot get access to IVF. He offered free IVF to couples who had no other way of getting it. He described what he was doing as an HIV vaccination study. If someone got pregnant and decided they didn't want to go through with it, they had to repay all the money that it cost for them to go through the protocol thus far. They had to give up rights to images and stories about themselves, etc., for his use in the press. Like, it was not good.
I think one thing that also stood out to me is I heard that, I don't know if this is true, you can see that, but he was marketing these people, he was like, hey, this is so you can protect your kid from HIV.
Yeah.
But the way that you protect a kid from HIV if the father of HIV is you just wash the sperm.
Correct.
Like, it wasn't actually to protect that from HIV, it was just like when they're adults, this will prevent them from possibly contracting HIV. It has nothing to do with the embryos getting HIV from the father in the
Correct.
embryo.
Yes.
And even though it was marketed that way, so it was like
Yes.
so unhelpful.
That is true. That is all true. There was a very low risk intervention to do the same thing he was doing by CRISPRing embryos. And by the way, he didn't successfully introduce the mutation he wanted in any embryos.
Even though he claimed to.
He claimed to that, yes.
So it's the scientific problem top of everything else.
Correct.
And it's alarming because he continues to just say
He didn't
like,
even do it.
ethics is holding us back, genome editing is the future.
Mhm.
He said he will be China to Darwin, like that's what he said.
Oh,
He actually said that. He actually said that. word
What
for
did
word.
he say?
I hope I'm remembered as the Chinese Darwin in 50 years.
So we have some personality disorder happening. All right. So, and he, said that he believed that he had followed that first report. So to your question earlier about the effectiveness of these reports, he was like, no, I followed that. I did what y'all said to do. And so that whole summit of people who had produced that thing were like, we were not sufficiently specific and directive. So they produced another report in which they were more specific and more directive, and provided what they hoped were, much clearer guidelines about this science. So it should not be considered until it's clearly efficient, safe, etc. Any clinical use should proceed cautiously, with initial uses restricted to a very limited set of circumstances that are set out clearly in the report, and that before any country approves the use, there should be national and international mechanisms to ensure that requirements have been met for initial responsible use. And it's not currently possible to define a responsible translational pathway for all uses, but any initial uses should be restricted not just to serious things that are there present at birth that couldn't otherwise be avoided, restricted to serious monogenic disease, common variants known not to cause disease, like you're switching to a common variant known not to cause disease, no unaffected embryos subject to editing and transfer, like there aren't any unaffected embryos available to you to use, and no or very poor alternatives for having a genetically related child without the disease. So again, trying to be much clearer. In parallel with this process, the World Health Organization also established a committee that was not looking at safety and efficacy, but rather at ethics and governance. And they produced 2 reports in 2021, one a framework for governance, and the other a set of recommendations. And again, this is the one that has had, my understanding is it's had traction issues. So this report defines what governance should look like here, what good governance looks like here. the values and principles that should inform both how decisions are made and what decisions are made. They developed tools, like specific governance tools. Again, everyone trying to be more concrete, because everyone was genuinely freaked out by a post saying, but I did that. And a bunch of examples and implementation guides. Their recommendations included, where's the establishment? The establishment of human genome editing registries. That's been really hard to get enforcement of. Like that's, there aren't really incentives for participating in that. There's not requirements for participating in that. So it's that, I don't think that that has been particularly successful. They also talked about international research and medical travel, right? If you're rich enough, you can go somewhere else and get it. Because the other thing in this space that is sort of background context is in mitochondrial transfer, which again I'll come to in a second. But the first time that happened, it was a doc from New York with a couple from Jordan doing it in Mexico. So, like, the scientific community has all of this stuff in the back of their mind when they're drafting stuff like this. Like they're not naive about how things are going to go down. And another, I think, important feature to point out about this is that they do, in fact, call for a regular review of the recommendations. Because as we've talked about the whole class, right, science evolves. Right, I think I showed you in my first lecture the original goals of the ELSI program, the Ethical, Legal, and Social Implications Program of the Human Genome Project, and made the point that they all still feel super relevant, right? And it's not because we haven't like solved any problems or had any insights, it's that the science has moved so much that now addressing those goals just looks very, very different than it used to. The same, that this last recommendation is acknowledging that the same will be true here. And another example of that is ISSCR. So we revised the guidelines in 2020, I want to say. The revised guidelines were published, and we have just published a revision to the embryo model piece of that because the science moved so fast that a year after we published new recommendations, we had to get back together and come up with new recommendations because the science had gotten so much further than expected. In the governance of science, that part can be challenging. They did it with the RAC, which is great. We did it with ISSCR. They're recommending it here. But this is a space where the distinction between hard law and soft law is important. So hard law is like what you think of when you think of law, like Congress did it, right? Congress created the law, we all have to follow it. Versus soft law, which is all the stuff that isn't legislative, right? So like professional guidelines, like practice guidelines, like institutional IRB recommendation or guidelines, et cetera. All of that stuff is much easier to evolve in response to new science. Something from Congress is much harder to fix because once it's there, it's like the political capital has been spent to do the thing and nobody wants to revisit it, right? So in emerging tech generally, which moves very, very quickly, it is often the case, particularly very early in the science, that self-regulation, as sort of flimsy as that might seem to some people, is often the best choice, like the best first step, is for the scientific community to get together and say, okay, we want to do this science, we get that it's controversial, and this is our effort to demonstrate to the public that we're being responsible. by regulating ourselves, by putting boundaries around what it is we will do to try to maintain public trust and avoid Congress being involved, because you really don't want Congress involved. Because of how sticky law is. Does that make sense? All right. And then 2 years ago, right about now, the third summit happened, and much less dramatic than the second one. And they largely pivoted away from germline genome editing. This summit was largely about somatic editing, because that's where the science is now. Like, we are actually demonstrating, we have FDA-approved therapies now, right? And one of the things we know about public approval is that if there are demonstrated benefits, folks are much more likely to be on board. Right? We did this survey years and years and years ago about embryonic stem cell research when that was under discussion by Congress in the mid-2000s. And we, the survey was quite long. Early in the survey, we said, do you approve of the destruction of human embryos for research to develop therapies? And people answered whatever they were going to answer. And then much later in the survey, we said, okay, tomorrow you wake up, USA Today, Wall Street Journal, New York Times, Washington Post, top of the fold. That's a thing that you have when you have a physical newspaper. It's the top of the fold. There is a treatment for diabetes that has been created with this science, embryonic stem cells. Now, how do you feel about this science? And there was a massive shift towards it. Right? If we demonstrate benefits to actual people, the public will, increases interest in the science. So we are demonstrating actual benefits to people in the somatic space, and that is where the third summit went to. So they did say heritable editing remains unacceptable. We need to protect legitimate research while preventing unproven and inappropriate use. And remarkable progress has been made in somatic genome editing. And we need to have a commitment to affordable, equitable access to the treatments that we already know are working. All right. For the last few minutes, I'm going to move to mitochondrial transfer, unless there are more questions and discussion that we want to have about this, which I'm totally happy to have. Any questions that haven't been answered? So mitochondrial transfer is in this weird space of is it germline, is it not germline? I assume that you all understand mitochondrial biology, right? Mitochondria are weird.
We also got Hillary.
Excellent, right? So different genome, all the things. Super complex because of the oddness that is mitochondria and their genome. Very complex mitochondrial disease, huge amount of variability. We don't have good tests, and we don't have good alternatives for avoiding mitochondrial disease in the next generation. So the idea is that you take mitochondria from someone who is healthy, transfer it into an embryo to replace the mitochondria with mutation, so that you can have nuclear genetically related next generation without mitochondrial disease. That's the
The fun thing is that they call it mitochondrial transfer, but really what the transfer is.
Yeah, no, absolutely. It's basically cloning, but we can't say that, so we call it mitochondrial transfer. I mean, most people call it MRT, mitochondrial replacement therapy, which is disingenuous because you're not transferring the mitochondria. You are transferring the nucleus, which I'll show you in just a sec. But that's why I call it mitochondrial transfer. What? It is. I mean, this is a place where scientists did a better job. The folks who wanted to call embryo models self-organizing embryo-like structures or souls. Yeah. Just no. All right, so there are two different approaches to this technology that have different ethical implications, and that's why I want to point out these two different approaches to it. So, zygote or egg, the red things are mitochondria with genetic mutations that you're trying to avoid passing on to the next generation. The little green with the squiggles are mitochondria from a donor, from a woman who does not have mitochondrial disease. So in the first one, pronuclear transfer, in this case, you take 2 eggs, one from intended genetic mom, one from mitochondrial donor. You fertilize both with dad's sperm. Have you learned about this? Did Hillary talk about this? No. Okay. You get them to the pronuclear stage, you enucleate both of them, and you transfer the karyoplast from the intended genetic mother into the fertilized egg of the donor. So again, to your point, you're not transferring the mitochondria, you're transferring the nuclear DNA. And then you trick it into thinking it's been fertilized and everything goes forward. And so now you have an embryo with intended genetic mom's nuclear DNA, donor woman's mitochondrial DNA. Okay? In this case, which is called spindle transfer, you enucleate at metaphase 2. You transfer the karyoplast in the same way into the enucleated donor oocyte. And then you fertilize it with dad's sperm and with ICSI, which I'm blanking on right now. It's where you inject the sperm straight into the blastocyst or into the egg, and that gets implanted in intended genetic mom. So in both cases, you're moving nuclear DNA, not moving mitochondrial DNA. But the way in which the scientific details matter ethically here for some people is that here you created 2 fertilized embryos and you're ending with only one. The other is getting destroyed, so you're destroying an embryo. Here you aren't destroying an embryo. So there are folks who are okay with spindle transfer and are not okay with pronuclear transfer. Does that make sense to folks? All right. So the uses of this technology include, of course, avoiding mitochondrial disease, but also potentially age-related infertility issues. So we have had, this is often called three-parent babies, right, in the press, in the media. And there are examples of this from the past. So in the late 90s, early 2000s, it became clear because a scientific journal article was published that a fertility clinic was they had this theory about women who were unable to who had chronic infertility, that the problem was their mitochondria was tired. And so they were taking cytoplasm out of the eggs of young, healthy women and injecting it into the eggs of women having challenges with infertility in hopes that they would juice them up. This produced a number of kids. So there are 3-parent babies walking around the world. And in the 2000s sometime, I think it was the New York Times, found a bunch of these families. And the way they talked about these kids was fascinating. They speak multiple languages, and they're brilliant at piano, and they do all these things, talking about them like they were super babies or something. But of course, these families are families who could afford this technology. These were just kids from rich families. That's all they were. They were not genetically special in
This
any
article
way.
about champagne is good for you. I don't know, it was just in the press. Some media thing, and I read it was like a study of many variables, and one was drink champagne.
And eat caviar.
And that correlated with really great outcomes.
And play polo. Yes. Yeah. Anyway.
Only the real champagne from France.
How very eugenic of them. Okay. So, yeah, it was the published paper about these kids was in 2001. There was a hearing in 2013 at the Human Fertilization and Embryology Authority. That is a body in the UK that it's a kind of regulatory body we don't have here in the US. It's called a QANGO, a quasi-governmental organization. I would actually love it if we had them here because they have legislative authority from Parliament, but don't have to go back to Parliament to change policy. So they are actually able to be responsive to evolution of the science in a much more nimble way than Parliament or Congress can do. So it was at that hearing that there was this question, this carving out of mitochondrial transfer from germline genetic modification. Because the fact is you aren't actually, you're not changing what's there, you're swapping parts. Which is in fact safer, arguably, in the same way that epigenomic editing is safer than actually making double-stranded breaks. There was also in 2014 a hearing at the FDA, and there was a National Academies, it was IOM at the time, now NAM, committee in 2015 that here in the US said, yes, this should be permitted, but only to produce boys. Again, to avoid the germline part of it. The UK said, that's sexist. And here's our regulatory structure. So they've actually been doing this in the UK since 2017, but it's you have to get a license to do it from the HFEA, but it has now been in practice for 8 years in the UK. Still not doing it here in the US because that's called germline, and the FDA isn't allowed to say if we've even gotten an application to do it. So I hope that sort of walking through this specific example gives you a bit more information and context about how it is the ethics and governance communities respond to new technologies, the role of scientists in the whole process, et cetera, and why sort of the scientific details matter very, very much to the ethical analysis. And that's it. Oh God, I'm 3 minutes over, sorry.
How many of you have ever heard of Gina Colada?
Gina Colada?
She is still a science reporter for the New York Times.
She's one of the very top of the line of people who commute
Communicate.
Communicate science to the general public. And our low motion population is very good at what she does.
Yeah. No, she knows. She knows our like. This one. These are two.
Yes. That's what they call icebergs.
Oh.
Okay, I'll remember when I got that. I had a very big
Business casual, business casual.
Oh, okay, now.
Yeah, hey, we can talk about whatever we want to talk about.
Yeah, I guess so. What time is it? Is that just now?
Did you put it out?
I'm not sure like all the